Hello, and welcome to our video for UVM Senior Design Group G, a novel method of characterizing lung function in mechanically ventilated patients with spontaneous breathing efforts. Our device works by inputting high-frequency oscillations into the breathing flow through a flexible membrane. Then, the pressure is measured at 3 different locations: upstream, downstream, and at the throat of a contraction. Using this information, the mechanical impedance of the patient's lungs can be calculated using an algorithm developed at the Health and Science Research Facility here at UVM. The ultimate goal of this device is to be able to measure the impedance of the patient's lungs. Here's our patient here, and we want to know if our patient has any kind of obstruction in his lungs that's causing that impedance to spike. So to do that, our device will enable us to measure the flow rate in the middle here, and we'll know the output conditions from the ventilator, and we'll know the impedance, the mechanical impedance of the ventilator and the mechanical impedance of the device, and using a Fourier transform we can use this information to calculate the impedance of the patient, which will then be provided for the medical staff. So this is how our device measures flow rate. This diagram here represents the critical contraction of our device, and if you have a flow coming in from this side here, we're going to be measuring the pressure at 3 locations: upstream, at the throat, and the downstream. And by having the pressure difference between the upstream and the throat and the downstream and the throat, using an algorithm developed by a PhD student in Health and Science Research Facility, we can compute the flow rate through this tube.
Alright, so here's how we plan on inputting pressure oscillations while maintaining a sterile environment for the patient. So we have an outer chamber surrounding a flexible membrane. With the outer chamber, we input pressure oscillations, and through the flexible membrane, maintaining a sterile boundary, the pressure is input into the flow, which we use to then take our measurements.
So we want to be able to measure pressures that are independent of the breathing of the patient. So in order to do that, we need to measure well outside the frequency range of breathing. So here on the x-axis we have frequency, and you can see here that breathing frequency is usually in about the 0 to 1 hertz range, but our input oscillations will be input in the range of 5 to 15 hertz, and the measurements will also be taken at that same frequency to ensure that the measurements that we get are independent of the patient's breathing.
Alright, so here's our device. We have the venturi tube on this side right here with the 3 pressure taps as we described before. On this side is where the patient will be breathing, and on this side is where the ventilator will be attached. So here's the outer chamber. On the top there is a port where we will input our pressure oscillations, and for ease of use we have this unscrew, where on the inside we have an O-ring to keep a pressure seal, and the latex sleeve which creates the sterile membrane.
What we have here is our data acquisition hardware. Our story begins with 3 Honeywell pressure transducers. They are silicon standard ceramic series gauge pressure transducers, and they are designed to measure from 0 to 250 millibars of pressure. Each pressure transducer will output a signal from 0 to 5 volts depending on the pressure that it reads. Because we are detecting oscillations, these output signals will be AC. As with all AC signals, they require filtering before being sampled and converted. So we have here 3 low-pass filters designed to cut off at a frequency of 60 Hz. Next, the signals are multiplexed and sampled by the Arduino microcontroller. We have found the sampling rate sufficient for capturing all 3 of our pressure transducers simultaneously. The next step is the XB transmitter. We are wirelessly transmitting serial communication from the Arduino microcontroller to the personal computer. Each signal is appended with an identifier in the microcontroller to tell which pressure transducer it came from. At the computer, we read the signal into MATLAB and separate it by which pressure transducer we have. With MATLAB, we may apply a bandpass filter to filter any frequencies below our oscillation frequency. That is, it is necessary to eliminate the power in the signals only associated with breathing. What we are primarily motivated to detect is any significant change in flow rate, as this would imply a patient requires immediate attention. To calculate for the flow rate, we use an algorithm developed by Baoshan Ma, and it tells us what the flow must have been.
Our pressure transducers are here. There's 3 of them. They read pressure differences with DC voltage outputs. They're calibrated with this manometer. The fluctuating DC outputs act as an AC signal and are filtered through here. This data is collected on the Arduino and then we read and manipulate it on MATLAB.